Hello, so today we'll be working on a problem of finding the moment of inertia of this object right here, a solid uniform triangular sheet with endpoints at 0, 0, B0, and 0h about the y-axis. And let's just go into it. So I is going to equal the integral of r perpendicular squared dm, and this is a small element of mass. So first, if we just quickly draw a picture of this. So it's going to be in the xy plane. Sorry about that. It's going to be in the xy plane, and it's going to look like this. Going to go up until h. Sorry about that. It's going to form a triangle like this with endpoints. This is going to be B, and this is going to be H, right? So now our perpendicular is just going to be, this is the, right here, this is the y-axis. So it's going to be what's ever perpendicular to that, which is, and this is just going to be x. See? So the point here is just going to be x. And so this is going to equal the integral of x squared dm. And now we need to find out what this is. And since it says it's uniform, that means this is going to be equal to x squared. And this is going to be dA times density. That's just what dm is. So it's going to be our density. Let's call that lambda. dA. And this dA right here is just going to be dx dy. So what is this lambda? So since it says uniform density, then it's just going to be mass over area. It's going to be some constant times that, but then we'll worry about that when it's like in the mass, So this is going to be mass per unit of area, and we can just bring that in front because it's a constant. So this equals, and I'll write this as a double integral. So it's going to be m over a times the double integral of x squared dx dy. And now we have to find our integration bounds. So let's go back up to here. And so let's say y, we can see y varies from this, and then x goes from this point to this point. So what I'm already thinking is on the bound of x, it's going to be 0 to b, because that's what x varies from. So then we got to see how y varies across those lines, and that's just going to be this. So this area, the line is going to be equal to, so y, this line right here, that's going to be equal to h minus h over b x. Since this is just point slope form, and then so we can see that y goes from 0 up until h minus h over bx, and then it continues like that. So then we can write this, that this equals m over a times the double integral, and our bounds is going to be, so x ranges from 0 to b, and y ranges from 0 to h minus h over b x, and this is of course going to be x squared with respect to x and with respect to y. So this is just quite easy to compute. So this is just going to be so there's no y terms. First, we have to integrate y first, so we can pull the x out, and it acts just like a constant, so we pull in front of here. And then integrating we pull this out, and then this is just going to be an inner integral. Just ignore this and this. So then this is going to be y evaluated. So that and that is just going to be y evaluated at 0 and h minus h over b x, and that's of course h minus h over bx. And so this is going to be m over a in front times the integral from 0 to b of x squared times h minus h over bx dx, and this is also straightforward to compute. It's going to be m over a times x to the 3 over 3h minus x to the 4 over 4h. There's a b there. Evaluated from 0 to b. So now we can just substitute b in, and then this equals m over a b to the 3h over 3 minus b to the 4 over 4. Oh no, so, and then there's a b here, so this cancels with one value here, so it's going to be 3, and there's going to be an h. So then we can, so this is, when we add these together, it's going to, this right here equals 1 over 12 b to the 3h. So then this equals b to the 3h m over a. But so one of our directions when solving this problem was find the moment of inertia of the object and express each answer as a number times mass and times a characteristic length squared. So then first what we can do is we can find the definition of mass. So mass equals the integral of dm. Oh, sorry about that. And this equals the double integral across just our area from here. So this is just going to be the same integration bounds. 0 to b, 0 to h minus h over bx. But this time we don't have an x squared, and we can bring our density out in front, m over a, since that's going to be our density function, dx dy. So we were given a problem that's uniform, so it's quite easy, so we don't have to worry about messy changes in density. So we can just bring it in front, and it's constant. So, and this equals, so the m's over here, they cancel. So then we can bring the a over here. So that means a equals the integral from 0 to b of the integral from 0 to h minus h over b x dx dy. So we could have also said that area was just equal to that. And instead of computing this integral, we could just go back here. And then its area is just the area of this triangle. It's just the area here. And we know how to compute the area of a triangle. It's just h times b over 2. So that means area equals h times b over 2. And then what we can do is we can substitute that into this equation right here. And that means this equation equals b to the 3h m over a, and a is just going to be h b over 2. So then this one term in h, this goes to 2, these h's cancel, and then we're left. Oh no, I missed a factor of 112 here. times 1/12. So then we just bring this 2 over here. So we get b squared m o 2 times this over 12. These just go to 6. And that's our final answer. Thank you for watching.